All right, here we go. This is the next lesson in the financial unit, and we're looking at the equation for compound interest this time. And so we have this example from the last lesson where the money grew. We had $1,000. It was vested at 6% per year and so on. So this is how the money grew. It's just the result from last time. So if we look at this, we have looked recently at how to look at how relationship in the numbers, how the numbers change, what the relationship is. Trouble with words today. So if we look at this, we could look at first differences, second differences, and so on, but we kind of know how this was calculated, right? We know that when we're going from one year to the next, we're adding 6%. And when we add, so we're adding 6% per year or each year. And so we can use previous knowledge to help ourselves with this a little bit, to even like think about what to guess for a pattern, because you'd have your $1,000 plus the 6% of $1,000, and we've seen something like this before where we said, okay, well that's $1,000 plus 0.06 of 1,000, and then you can take that 1,000 out front and write it as 1 plus 0.6. And so you've seen this in the past where you're calculating tax. You can just multiply by 1.13, in this case 1.06. So it shouldn't be a huge surprise that we end up with a common ratio. So if we look at the ratio here, if we did our 1,123,60 divided by the 1,060, and in fact, you could think about, we started with 1,000, right? So this is at the end, right? At end of year one, at end of year two. So the 0 is your starting. And so we could even do the ratio of the beginning ratio, which is really obviously, so the multiplied by 1.06. So this one here is, we're multiplying by 1.06. And so was this one, because this one would have been 1,060 divided by 1,000, which would give 1.06, obviously, because the decimal place would just move 3 spots, right, when you're dividing by 1,000. Anyway, so each of these along the way is a multiply by 1.06 when you do the math. Just dividing the second one by the first one all the time. And so we see we have a common ratio. And so if we have a common ratio, we can conclude that this is an exponential situation. So it is an exponential relationship, or just relation, sometimes people say. So it's an exponential relation, which we remember the equation for that is like y equals a and then b to the x. Don't even need the brackets really, but it's a b to the x. Kind of helps make you see that just the b is on to the exponent of x. This is your initial value, which in financial situations we call it the principal. So your initial value, which in this case is the principal. You have in here your common multiple, just like before, right? In this case, that multiple is 1.06. So obviously that is 1 plus your r as a decimal, your rate, your interest rate as a decimal. So 6% is your 0.6. And up here is just your number of years and so on, right? And this is the value of the investment or the amount. So value of the money or the amount, right? So you can picture this being like an A, and this being a P, and this being a 1 plus I, and this being a T. You're looking at what variables are typically used to make those different color, make them stand out here. So that won't be many surprises on this page then, right? So it's going to be the equation we just showed, where A is your amount, B is your principal, and so on, right? So notice the amount is a little different in this case. The amount we get directly from the equation. So rather than calculate the interest before, we had like A equals the principal, the amount equals the principal plus the interest, which is still true, but we actually calculate the amount directly in this. So this is calculated directly, which is pretty handy, right? So yesterday in the last lesson we did calculation step by step for the first 5 years. But if we thought about like trying to go to like the 20th year, like how much do the calculations all the way out to the 20th year of this, you'd have to literally do all 20 rows of calculations. Whereas now we'd be able to just put a 20 in for the number and calculate the amount after 20 years directly. So that's the power of this one. Okay. Notice that the interest isn't really something we're calculating directly anymore, so it's kind of missing, but we can use that same equation as before. So they show this in the textbooks as a separate equation, but really you're just subtracting P from both sides and just solving for I. So subtract P, you get I equals, or the interest equals, the amount you end up with, take away what you started with, which just makes sense, right? The amount you end up with, take away what you started with, is going to be how much interest you earned, right? If you invested 10,000 and you ended up with, I don't know, 12,000, take away 10,000 is the 2,000 you made in interest, which would be pretty sweet. All right, so that is the stuff. So when we look at this question, you would write down, or at least notice what you're given, right? So you're investing this much, so there's your amount, and it's at this, so that's your rate, that percentage, and it's for this many years, right? So if you are doing it off to the side, which doesn't really add a ton here, obviously just noticing it, right, is the key. So we have the 5.7%. Don't forget to write that as 0.057. And of course, what we're doing there is we're dividing by 100, which is literally what percent means. Per means divide, and cent means 100. And T equals 4, right? So we just use our equation, A equals P1 plus I to the N. And we put our numbers in. We have $3,000 at 1 plus 0.057, all to the power of 4. And obviously BEDMAS is used here where you do what's in the brackets first. So 1.057. So we did the brackets, and then the exponent's going to be next. So first, second. So let's do the exponent. Notice the exponent is just on the 1.057. Get pretty crazy numbers if you did the power of 4 on the 3,000 also. So 1.057 to the power of 4, right? Power of 4 gives us a 1.28. I learned a new trick. I don't know if I'll be able to do it with that. Oh yeah, it looks like it. Oh, it's not really working. I'd have to use my mouse to do it. I was trying to do it on the smart board, but realized I could copy and paste from here. Not that it's speeding things up much right now, but it helped me the other day. And so we have that, and then we just do that multiplication. So we have that number in the calculator already. I'm using all the decimals. Times 3,000 equals 3,744 and 4 cents, rounding to the nearest cent. The nice thing about this is you're not worried about, or you don't have like rounding in all of these different steps along the way, right? So this is for 4 years. So we've been 4 lines of calculation step by step, which would still give about that same number, right? But after 1 year, 2 years, 3 years, and 4 years, and you calculate your interest each time and your amount each time, and do all these numbers, all these calculations all the way along for all 4 of those years, you'd end up getting something approximately similar to that, okay, depending on how many decimals you keep. Banks would keep 7 decimal places, which means that they're good to the nearest cent, basically. So calculate the amount of interest earned. Well, we know that the amount equals the principal plus the interest, or in other words, interest equals the amount minus the principal. I'd kind of rather you not think of this one as a new one to remember, right? You can still just use this one that you already know. Less things to memorize is always good, right? So 3,744.74. Take away the original 3,000 that we invested. Obviously, it gives us pretty easy numbers to do here. 744.74. Right? So obviously, in this kind of question, therefore, the interest earned is $744.74, and up here we would have had a therefore the amount of the investment is $3,744.74. How much money you'd have to be able to take out of the bank at the end, right? So we did some legwork to get an equation, some analysis, used our exponential knowledge, right, to be able to get an equation, and then it makes our life easier because we have the power of that knowledge now. So with loans, interest grows the exact same way, except that the interest rates are different. So interest rates for borrowing are always bigger than the interest rate for investing, because that's just how it works, right? The people that you give your money to hold in your bank account, they use it to lend out, so they're not going to give you more percentage than they take in. Wouldn't be a very good business model. So this question here, if we had $26,000 borrowed at 15% per year, that's well, you know what? If you look at 15%, you think that's bad, but credit cards, last I checked, they were like 29.9%. I think they're even more now. So 15% sounds bad, but credit card debt's even worse. And not only that, they don't calculate annually; they calculate interest daily, if I remember correctly. So they're adding interest in even more often, which means you're going to grow even more interest as a result of the compounding. So determine the amount after 8 years. And so we're just going to do our normal stuff here. We've got our principal that we've invested. We've got our rate, and we've got our time. So we have our A equals P times 1 plus I to the T. Is that what we did? I feel like I did an N by accident. The other one, we had said, yeah, but it is an N. So I was saying T before. That's where the mistake was. This is actually an N, but obviously just however it's defined doesn't matter. So just use the N. Depends on which textbook you're looking at. Obviously, it's where the number is that matters, not what the letter is. So the 26,000, the 1 plus the 15%, so 0.15, convert it to a decimal, and the power of 8. So this would have 8 rows of calculations where you get the interest added on, get the new interest, add that on, get the new interest on that, bigger number added on, and so on, right? 8 full lines. Whereas here, all we have to do is the 1.15, the power of 8. So 1.15 power of, that's not the right button, clear that. 1.15 power of 8. That, so 30590. So 30590. I'll say, I always like to indicate that I'm keeping more decimals than that. So then we just multiply by 26,000. So rather than keeping lots of decimals, that is the wrong number. Which one's one of these I think just fixes one step, and another one gets rid of everything. I chose the wrong one. 1.15. The power of 8 times 26,000. So we're looking at having $79,000, 534 and 59 cents be the money you owe if you just let that money grow. So therefore, after 8 years, you would owe $79,534.59. That seems like a lot, but it happens. If you mortgages on houses, the general result that's typically true with mortgages and houses, if you mortgage a house for 20 or 25 years, if it was a, say, $500,000 house, you're going to end up spending about $500,000 in interest. So you end up spending $1 million on the house over the 25 years. Lots of interest getting paid. People don't realize, or realize, but try to ignore maybe. Cost of borrowing, obviously your amount equals your principal less your interest again. And so our interest would just be the amount minus the principal. I'm just going to keep showing it like that so we don't have to realize or remember a new equation. So if I just flip that equation around, we'd have I equals the amount, which is the 79,534. Take away the original of 26,000. So that would give us, I still have that number in, which is good. Take away the 26,000. And so we have 53,534.59 in interest. So I'm just going to say, and the interest paid is $553,534.59. That mortgage paying double bit is based on sort of current rates. Just so you know, as rates go up, interest goes up a lot. So that is sort of different though, because that's where we're talking about payment plans and so on, where this is just a loan where you just pay it off at some point. So that is it for that. You can see how the equation works, how you can get the value after any number of years. Let's just do a quick calculation here and have our amount equals our 1,000 times the 1.06 to the power of 5. So let's just confirm that 1338 number. So the 1.06 to the power of 5 gives you that, and we multiply by 1,000. Original amount of money, and there's our 1338.23. It actually is. We had rounded along the way, very depending on what numbers we kept. You look at the number that you get from keeping a whole bunch of decimals, really would round to 23, unless you use the even odd rounding rule that banks use, which it would be actually the 22. Anyways, the extra rule for rounding is if you're rounding a 5, this third decimal place, then you would keep an even number. It makes it so you don't round up more often than you round down. I'll show you more about that if anybody's interested, but otherwise just round kind of normally. So you can see that it works, and that's about it. So as usual, your practice questions are on the first page. Let's get those submitted, of course, and if you have any questions, let me know. Otherwise, thanks for watching.